Imagine a massive factory, a beating heart of energy production. That's your steam power plant. It's an incredible machine that takes a fuel, usually coal or natural gas, and uses it to boil water into high-pressure steam. This steam then spins a massive turbine to generate electricity, lighting up our homes and cities. It sounds clean, efficient, and powerful, right? It is, but this whole process of burning fuel leaves behind a messy secret, especially within the giant furnace known as the boiler. It's like running a fireplace non-stop. You get ash, sticky residue, and, you guessed it, a lot of soot. This isn't just an aesthetic problem. This buildup, often called slag or fouling, acts like a stubborn blanket of insulation. It coats the crucial boiler tubes that are supposed to absorb the heat, slowing down the heat transfer and making the entire plant less efficient. Eventually, if left unchecked, it can even damage the equipment or cause a dangerous soot fire. That's where our unsung hero steps in. Meet the Sootblower, a somewhat boring name for such an essential piece of equipment. Think of it as a specialized, high-powered cleaning arm for the inside of the boiler. It's not some guy with a massive pipe cleaner. It's a sophisticated mechanical system built right into the boiler walls. Its sole purpose is to blast away the soot and ash deposits from the heat transfer surfaces, the boiler tubes, superheaters, and economizers to keep them sparkly clean, or at least clean enough to work correctly. Most commonly, soot blowers use a powerful, focused jet of medium, typically superheated, steam, the very steam the plant is making, or compressed air. Why superheated steam? Because it's readily available in the boiler, and critically, it's dry. Using wet steam or water could potentially cause thermal stress or erosion to the hot steel tubes, which is a major no-no. The soot blower isn't a one-size-fits-all tool. The interior of a massive boiler is a harsh environment with varying temperatures. You have different types designed for different zones. In the hottest part of the furnace, the main combustion chamber, you often find wall blowers or short retractable soot blowers. These have a short nozzle that pokes in through the wall, performs a quick, powerful blast of steam in a wide arc, and then immediately pulls back out of the heat zone. In the slightly cooler areas, like the convection pass where the tubes are tighter, you use long retractable soot blowers, LRSBs. These LRSBs are the big guns. They extend a long rotating metal pipe, sometimes 20 or 30 feet, into the boiler. As the pipe or lance slowly moves in, nozzles along its length rotate and fire high-pressure steam jets in a spiral pattern, sweeping the entire tube bundle before retracting back to safety. It's a precisely choreographed cleaning dance. The soot blower isn't just turned on haphazardly. Its operation is a carefully managed process, known as soot blowing cycles or programs. Well, imagine you're on a cleaning schedule, but this one is dictated by real-time boiler conditions. Plant operators constantly monitor factors like the temperature of the flue gas, the steam temperature, and the draft air pressure within the boiler. When these parameters start to drift, a telltale sign that too much soot is insulating the tubes, it's time for a cleaning cycle. The system is usually automated, running on a sequence, perhaps once a shift or multiple times a day, depending on the fuel quality and load. The goal is a balance. Clean the surfaces enough to maintain efficiency, but not so much that you waste the valuable high-pressure steam, or worse, cause unnecessary erosion to the tubes. It's a constant low-stakes battle between power production and cleanliness. So, why go to all this trouble for a little soot? The payoff is huge and directly impacts your wallet and the environment. First, efficiency. A layer of soot as thin as an eggshell can dramatically reduce the boiler's heat transfer efficiency, forcing the plant to burn significantly more fuel, coal, gas, etc., just to produce the same amount of electricity. Keeping the tubes clean means the boiler needs less fuel, which directly lowers the plant's operating costs. Second, plant availability and safety. Soot buildup can cause localized overheating or even lead to tube failure, forcing an expensive and unplanned shutdown. By preventing excessive fouling, soot blowers keep the plant running reliably, avoiding costly downtime. In short, these simple devices are fundamental to modern power generation, ensuring we get our electricity efficiently and without major interruptions. Once the soot blower blasts the deposits from the tube surfaces, the dislodged material doesn't just vanish. It falls down into the ash hopper at the bottom of the boiler or gets swept away by the flow of flue gas. The large chunks are collected and removed, while the finer particles continue to travel with the exhaust gas toward the plant's environmental equipment. This often includes electrostatic precipitators or baghouses, which are designed to capture the fly ash before the cleaned flue gas is released through the smokestack. So the soot blower isn't the final step. It's the critical first action in a chain of processes aimed at keeping the plant running efficiently and cleanly. It's a reminder that even the biggest, most complex machines rely on regular, high-tech housekeeping to keep the lights on. Alright, so we've talked about how a soot blower acts like a high-pressure toothbrush for a power plant's boiler, blasting away the nasty ash and soot to keep things running efficiently. But what happens when that toothbrush itself needs maintenance? When you see a soot blower taken apart, just the main body or carriage unit, sitting on a shop floor, it suddenly goes from being a mysterious box on the side of the boiler to a fascinating piece of mechanical engineering. What you're looking at is a complex assembly designed to perform a very precise, yet brutally forceful job in an extremely harsh environment. The large cylindrical housing is the protective shell, but the real magic is inside. First, notice the lance tube. Connection. That's the long pipe that extends into the fiery boiler. Its condition tells you how much abuse the machine has endured. Next, you'll see the carriage assembly, a robust frame that drives the lance tube. This carriage is home to the motor, often a hefty electric motor, which provides the muscle. This motor doesn't just push the lance in and out, it powers a specialized gearbox. This is the heart of the movement, engineered to do two things simultaneously. Axially move the lance in a straight line, the travel, and rotate it, the sweep. This synchronized spiral motion is absolutely critical for effective cleaning. Look closely, and you'll often see the poppet valve at the steam inlet, a critical component that controls the high-pressure cleaning medium. This valve must open and close precisely at the right time to prevent erosion and conserve steam. Finally, the whole assembly sits on a track or mechanism that lets it be inserted and withdrawn smoothly. Seeing it disassembled is a great reminder that these silent sentinels of efficiency are tough, intricate machines, a combination of raw power and pinpoint precision, built to withstand the heat so our lights stay on.